Welcome to the Hitchhiker's Guide to Calculus. My name's Kevin, and I'll be your guide to Chapter 1.11, Types of Discontinuities. Now, there are three different types, and we'll start with what we call the jump discontinuity. I think it's easiest to see from a piecewise function, so I have a piecewise function defined over here. And just as a reminder, we might as well try to graph it to see what it looks like. The top piece of our piecewise function is x plus 1 squared. That's just a quadratic, so a parabola shifted to the left one. Since our piecewise function tells us we're only to graph this function for x values less than 0, we're going to stop at 0. It is less than or equal to 0, so we'll put a solid dot there to tell where it stops. And then we'll graph the bottom part of this piecewise function, negative 2x plus 3, which we know to be a line with a y-intercept of 3 and a slope of negative 2. Since it's just x is greater than 0, we need to put an open circle where it begins. We'll model the slope here going down 2 and to the right 1, connect our dots, and you can see that our graph has a giant gap in it, hence a jump. We're jumping from one part of our function to another part of our function because our y values are different where we switch from one function to another. If we wanted to algebraically demonstrate that a jump was occurring, we would take a look at the limits. And we're going to check out the limit as x approaches 0 from the left of our function and the limit as x approaches 0 from the right of our function. And we'll notice that the two y values are going to be different, indicating that our function had to jump at that x value of 0. When we evaluate the limit as x approaches 0 from the left, that tells us we can plug in 0 to the upper part of our function where x values are allowed to be a little bit less than 0. So 0 plus 1 squared would get us a y value of 1. And we know that already. We graph the function. Look at where our function's going, a y value of 1. For the bottom limit, as x approaches 0 from the right, we'll plug 0 into our bottom part of our function. Negative 2 times 0 plus 3 will get us 3. And we already know that from our graph, we saw that our right side of our function is approaching a y value of 3. And since both of these limits do not equal each other, this would be a perfect algebraic demonstration of a function with a jump discontinuity. Now let's slide on over to our second type of discontinuity, a removable discontinuity. I think this one's easiest to see when you look at a rational function that can be simplified. With rational functions like these, we always have to be aware that factoring can take place and maybe we can simplify in one way or another. And this is exactly what we can do. For this function, if we factor the numerator, we see that it's going to be x minus 3 times x plus 1, all divided by x minus 3. And since there's an x minus 3 in the numerator and denominator, I can hack these out of here, essentially removing those factors from our function. Now, since x equals 3 was a value that I'm not allowed to plug into our function because that would make our denominator 0, we have removed that bad point or removed that discontinuity at x equals 3, leaving us with just the function x plus 1. And we know what that looks like. That just looks like the equation of a line. So we can graph it, but there is going to be something funky happening at x equals 3. If we go to graph this line, x plus 1, it has a y-intercept of 1 and a slope of 1, so it would go up and to the right, down and to the left, just like this. Right. However, at x equals 3, we remove that discontinuity, and that is always going to create a hole for us. So on our graph at x equals 3, we'll have a hole. And now you might need to find the y-coordinate that's associated with it. So if you ever need to find that, you just go ahead and plug in 3 to the function after you've simplified it. So f of 3 here would just be 3 plus 1. That'll be 4. So 3, 4 would be the coordinates of our hole. So we can go to our graph and throw in a little open circle there at the point 3, 4. And let me go in there and clean this up a little bit. But once it's all said and done, that hole right there is going to be what we would call our removable discontinuity. Our function's continuous everywhere else except at that hole at 3, 4. With all that being said, I think it's time to move on to our third type of discontinuity. This type is known as an infinite discontinuity. I think the easiest way to see it is again to look at a rational function but one that can't simplify at all. This x plus 2 over x minus 1 is a good example. We can't factor that. We can't reduce it. So what can we do? We can notice where this function is not continuous. It's not going to be continuous at any x value that's going to make the denominator 0. We know we can't divide by 0. So we can at least say that x is not allowed to equal 1. And if that piece of our function is never going to be reduced or simplified out, then we would call this a non-removable discontinuity. And every time you have a non-removable discontinuity, you're going to create a vertical asymptote in your graph. And we know when we have a vertical asymptote that our function likes to go up that asymptote to infinity or down that asymptote to negative infinity, hence why we call this type of discontinuity an infinite discontinuity. Now, if we went on to graph this function and take a look at it, using some skills from pre-calc and finding the horizontal asymptote and plugging in some points, you would see that your graph ends up looking a little bit like this. On the right side, we've got a piece that goes up to infinity and over along a horizontal asymptote at 1. And on the left side, we have a part of our function that's going to go down as it approaches our vertical asymptote. Hence, we can evaluate a couple limits as x approaches 1, one from the left and one from the right. And as x approaches 1 from the left, we can see that our function approaches the vertical asymptote and goes down, so it's going to go to negative infinity. And as x approaches 1 from the right, we can see on the right side, our function approaches our asymptote and goes up, so it's going to go to positive infinity. That takes care of all of our different types of discontinuities, so make sure you check out our next video popping up now about how do we make sure a function is continuous at a point. Don't forget to hit subscribe and like the page to get alerts about all the content we release each week.